Number 12, determine if the table shown is linear, exponential, or quadratic. If it's exponential or linear, write the function that represents it as well. You do not need to write the function for the quadratic table. So assuming one of these are quadratic, you do not have to write the rule or the function for that particular table, but you will have to write one for exponential or linear. So across the top here, we're just indicating, is this table linear, quadratic, or exponential? And the way we do that is checking the first differences, the second differences, and if none of that works, then we need to check for a common ratio. So the difference here is 243 to an 81. That is a decrease, so a negative. So 243 minus 81. So 243 minus 81 is a decrease of 162. From here, 81 to 27 is a decrease of 54. So minus 54. From 27 to 9 is 27 minus 9 is minus 18, and then 9 to 3 is minus 6. So in finding the first differences, I can definitely tell they're not the same, so I can eliminate linear. Linear is the first difference, so the first difference would be linear. Next thing to check in my eyes would be the second differences, which is testing for quadratics. So from negative 162 to negative 54, so negative 162 minus negative 54. Actually, no, that's not right. Negative 162 minus 54, no, 54, geez, 54 is a change of 108. So 108, and it's a positive 108 because you're going from 162 to 54 in the negatives. From 54 to 18 is a difference of, or negative 54 to negative 18 is a difference of 36. And from 18 to negative 6 is 12. So the second differences are not the same. So if it must be one of the three, then I'm pretty sure this is going to be exponential. But rather than just assume, I'm going to make sure that I can prove it. So to find an exponential, you take the second term and divide it by the first. So you would do 81 divided by 243. So 81 divided by 243. That gives you this decimal. Now you can write that as the function, but it's not going to be very helpful when we go to write the function. So what I suggest you do is hit math, enter, enter, and it changes this decimal to a fraction. So it's multiplied by 1/3. So from here to here is being multiplied by 1/3. Now I'm going to check the second or the third point here. So I do 27 divided by 81. So 27 divided by 81 gives me the same decimal. Math, enter, enter, 1/3. So it's being multiplied again by 1/3. And 27 to 9 is multiplied by 1/3. 9 to 3 is being multiplied 1/3. So now I have a common ratio of 1/3, which means this is an exponential decay function. Now, I think Actually, you're probably good just indicating it's exponential. You don't even have to worry about the decay part. Just remember that if it's decreasing as you go, it's exponential decay, not exponential growth, but that's beside the point. Next, we want to write a function for this exponential table. So remember that the standard form of an exponential is y equals a times b raised to x. So y equals a times b raised to x. A is always the initial value, so where you begin, and b is the rate in which it's changing, which we found to be 1/3, and then x and y stay the same. So the initial value is going to be 243 multiplied by 1 divided by 3 raised to the x power. So I'm plugging this into my calculator just to see if I can plug it in and match my table, because sometimes tables can be misleading. And so, for example, here I have my function, so 243 times 1/3 raised to the x power. I'm going to go ahead and hit table. And if I scroll back up, so scroll back up to match 0 here, where x is 0, y is 243. When x is 1, y is 81, 27, 9, 3. So it checks out. So my answer is this function. So again, 243, because that's where my table started, the initial value. So y equals 243 times 1 divided by 3 raised to the x power. Remember that this term is the first term. This term is what it's being multiplied by each time. And then x and y will just always be in that position. Part B, looking for, again, starting from scratch, you're looking for the first difference, then the second difference, and then the common ratio. So here it is adding 3, here it is adding 5, here it is adding 7, and here it is adding 9. So the first differences are not the same, so it is not going to be linear. So next I'm going to check for quadratics. This is +2, +2, and +2. So here I have the same second differences, and the same second differences indicates that this is going to be a quadratic function. And remember, you don't have to write a function for quadratics, mostly because it's way too complex and difficult. Oh, not difficult, but convoluted, and you don't need to know it for your test, so we're not going to make you do it for your review. And then C, I'm going to guess, since I have exponential and I have quadratic, I'm going to assume this was a linear function, but I'm not, again, just going to leave it at my assumptions. I'm going to test it out. So from 4 to 9 is +5, +5, +5, and +5. So all my first differences are the same. So this is a linear function. It's a linear growth, but again, you don't need to know that. Keep in mind that linear functions are always y equals mx plus b in terms of their standard form. Y and x are always in the same position. Before x, you have what it's changing by, or the slope. So it's changing by 5 each time. So 5 will go there. After this plus sign is the initial amount, or the y-intercept. So where x equals 0, y is 4. And so there is your function or your rule for that table.